In this video, we'll look at when are functions even, odd, or neither. We'll start with when is a function even. Graphically, a function f is even if the graph of f is symmetric with respect to the y-axis. So here's an example of a function. We know it's a function because it passes the vertical line test. Each input is mapped with exactly one output. And we look at the y-axis. Is there symmetry with respect to the y-axis? There is. Therefore, we state that f of x is even. Now, algebraically, we can say that a function is even if and only if g of negative x is the same thing as g of x. So here's an example. G of x equals negative 4 x squared plus 1. Now we'll determine what is g of negative x by substituting negative x in place of x. Now we'll simplify. Negative x, quantity squared, is equal to x squared, which when multiplied by the negative 4 equals negative 4x squared plus 1. Since our result is exactly the same as what we started, then we can say that g is even. Next, we'll look at when is a function odd. We don't want you to develop a misconception that a function is odd if it's symmetric with respect to the x-axis, because, as you know, that's not possible with functions. Functions must pass the vertical line test. If a graph was symmetric with respect to the x-axis, it would not be a function. So there's a different definition of when is a function odd. Graphically, a function is odd if the graph of it is symmetric with respect to the origin. That's a little bit harder to spot visually, graphically. So we'll start with the algebraic case. Algebraically, a function j is odd if and only if j of negative x is equal to negative j of x. In other words, when I substitute negative x in place of x in the original function, if I end up with the opposite of what I started with, then this function is odd. So we'll check this out right now. Let's substitute negative x in place of x. Now let's consider negative x quantity cubed. That would be negative x times negative x times negative x. That would be negative x cubed. And when I multiply two negatives, I get a positive. You will notice that my result is the opposite of what I started with. Therefore, we can state with confidence that j of x is odd. Next, we'll look at the graph of a function and determine if it is odd. So one thing you will notice is as the left end tends toward negative infinity, the right end tends toward positive infinity. That's an indicator. If you were to find individual points on this curve, you would notice that there are also points. So if you look at a point like x, comma, y, you would find that another point, negative x, negative y, is also on the curve. So this particular function, h of x, is odd. Here's a specific example from the homework. Is this function even, odd, or neither? Remembering what we talked about with even, remembering we're going to substitute negative x in place of x and see if the result is equivalent to the original function. If so, the function is even. We'll start by assuming it's even. We'll put negative x in place of x. Now we'll simplify. And we notice that the result that I get for f of negative x is equal to the original function. Therefore, this particular function is even. We'll also recall that even functions are symmetric across the y-axis, or with respect to the y-axis. So I graphed this function using Desmos, and we'll verify that it has symmetry across the y-axis. So this function is even.